Okay, so today we're going to be starting matter. So we're going to be going over in this unit matter in nomenclature. So some of this will be review from other classes. Some of this will be new. The nomenclature portion is extremely important throughout the year. So just make sure you're doing a lot of practice when we get to that, because in future units, I will expect you to be able to write the formula and then solve the problem. Okay, so when we look at matter around us, most of the stuff that we see around us is a mixture either of pure substances or more likely compounds. So, so these mixtures can be sorted into substances. These, like I said, are usually compounds. Sometimes there might be elements, but not as frequently. And these compounds can be broken down into the pure elements, which we see on our periodic table. So, like I said, first thing you want to think about when you're thinking about matter is if it can be physically separated, you have a mixture. So, if your answer is yes, that's a mixture. If it cannot be physically separated, you have a pure substance. And these pure substances can be either a compound or an element. So, first of all, we're going to be going over the difference between these and then like how you can separate mixtures and so on. Okay, so the pure two types of matter, like I said, are either pure substances or mixtures. So pure substances can be an element. These would be composed of identical atoms. And just examples of things you have around the house, which are pure elements, are things like your wiring in your walls, your copper wiring, or if you get out some aluminum foil to wrap something up, that is a pure aluminum, an element. Compounds are going to be composed of identical molecules. So these are going to be composed of two or more elements in a fixed ratio. So some examples of these are going to be table salt. And if you notice, these are the properties of these, like table salt is going to be different from sodium and chlorine. So if you remember from the periodic table unit, I told you guys chlorine is extremely poisonous. It was used by the Germans to gas troops during World War One, so extremely dangerous. Sodium reacts violently with water, but when you combine those two, they both become stable to form sodium chloride. And that's that, the only thing you have to worry about there is that just taking too much of that, maybe raising your blood pressure, but it's not going to be something that would kill you outright. So first, let's go over the difference between a mixture and a compound, how these two are different. So mixtures are going to be a variable combination of two or more pure substances, and they can be physically separated. So here we have a piece of granite. Some mixtures are going to be solids, and it has different minerals in it. And we have some apple juice. So when we talk about a variable combination, you think about if you have salad dressing, you can use maybe different types of oil in the salad dressing, maybe use olive oil or vegetable oil to make your salad dressing. You can use different types of vinegar, maybe red wine vinegar or apple cider vinegar or just white vinegar. And you can also add different spices to your salad dressing. So, and if you don't like a particular spice in your salad dressing, you can always take that out. So we could physically separate it, and the combination might vary, but it will still be salad dressing. So if you add more oil or less oil, it's still salad dressing. It might taste a little different, but you're not making something totally different. On the other hand, compounds always have the same composition no matter what, no matter where you get it from. So here is just some water. It's going to be the same no matter where we get it. If we get it from the fountain in the building, or if we get it from maybe from a lake or a river near us, or if we get it from the ocean. So it's always the same elements in exactly the same proportion by mass, no matter where you get it from. So something here is if we look at compounds, here we have carbon monoxide, carbon dioxide. You notice here we have very, very different properties. Carbon monoxide has a 1-to-1 ratio of carbon and oxygen and is poisonous. Carbon dioxide has a 1-to-2 ratio of carbon to oxygen. It's not poisonous. Maybe it can lead to global warming, things like that, but it's not something that's going to kill you outright. You vary the composition of your salad dressing, though, it's not gonna become poisonous, but small variation in your compound makes something completely different, which may not be good for you. Another thing, like I said, compounds have to be chemically separated, whereas mixtures can be just physically separated. So I want to show you two videos which will show you how compounds have to be chemically separated or chemically put together, just to give you an idea about that. Okay, so what I want to show you with this video is a synthesis of water. So the synthesis of water is a very violent reaction between hydrogen and oxygen. And in this video, what you're going to see is a balloon that's filled with hydrogen gas. When the balloon is lit using a wooden splint, it will react violently with the oxygen in the air and produce water vapor. Now, since water vapor is a gas, we don't see the water vapor in this experiment, so that is just goes up into the air, but you can see the really cool explosion here. So let me play this. So last video that you guys watched was the synthesis of water from hydrogen and oxygen gas using a chemical reaction. So that was a very exciting chemical reaction. And now we're going to watch the decomposition of water, which means we're breaking water apart into hydrogen and oxygen gas using another chemical reaction.
If we connect an electrolyzer filled with distilled water to a source of direct current, we can observe a slow evolution of gases. After some time, we notice that the volume of the gas released at the cathode is double that of the gas formed at the anode. To identify the gaseous products of the reaction, we collect each gas in a test tube and check its behavior in the presence of a glowing splint. The characteristic cracking sound proves that the gas released at the cathode is hydrogen. The ignition of the glowing splint is evidence that the gas collected from the anode is oxygen, which supports combustion.
Okay, so hopefully in the videos you guys could see that like when we have compounds, we have to either do a chemical reaction to either make them or separate them. Mixtures, though, if we have salad dressing, we don't like a particular spice, we can always filter that out or do something else to get rid of that in the mixture, and we could go through a physical separation to get that out. So if you have a sample in the lab, I want to show you one way that a chemist would be able to tell, at least to start to see if they have either a mixture or a pure substance. So we're going to look at something called a heating curve. So here, I want you to draw this in your notes. But what I want you to see here is that what we have on the y-axis is the temperature. On the x-axis, we have the time. So if you can imagine, if you're heating something up, what this is showing you is at the beginning, if you were to start with a solid, at the beginning, you would see that the temperature of that substance was changing as time went on. So the solid would be getting warmer and warmer and warmer, but still be a solid. Eventually, your substance would start to melt. So here, what I want you to notice is as it is melting, the temperature now is staying constant. It's not changing as time goes on. Again, once it's completely melted, now you have a liquid, and now the liquid is starting to warm up. So, as you see again, if you look at the y axis, the temperature is now changing once again as this liquid is warming up and it's completely a liquid. So now you have a liquid getting warmer and warmer and warmer and warmer until it reaches the boiling point. Now, when the liquid reaches the boiling point, what I want you to see here is now once again, the temperature is staying constant as it boils. So here we have the liquid boiling, the temperature is not staying, we have a plateau. Once the liquid is completely boiled off and turned into a gas, once again, if you look at the y-axis, you will notice that now the temperature is changing once again as the gas heats up. So I want to go through this and just label a few things on here. So hopefully you have that drawn in your notes. And now we're going to go through and label some stuff on this. Okay, so now I want to go through and just label this curve. So on the side here, what I want you guys to write in your notes is to write down two terms, kinetic energy. This is energy of motion. And we're going to abbreviate this as KE. And potential energy, this is energy of position. And we're going to abbreviate this as PE. You think about if you're riding a roller coaster, when you're at the top of the hill, you have a lot of potential energy because you're very far off the ground, but the car isn't moving. But as the car goes down the hill, all that potential energy is turning into kinetic energy, and you have a lot of motion at that point and get really fast. So here, when we look at this curve at the beginning, as the solid is heating up, the temperature is changing. And the reason why the temperature is changing is because the molecules or atoms in that solid are moving faster and faster and faster. So we say the kinetic energy is increasing. And kinetic energy is related to the temperature. The higher the temperature, the higher the kinetic energy. As we start melting our solid, the temperature is not changing, so the particles are not moving any faster during this transition, but the particles in that solid are spreading out. When they're solid, they're very closely packed. When they're liquid, they're further apart. So during this time period, those particles are spreading apart in order to form a liquid. So potential energy now is increasing, but the particles are not vibrating any faster. Here, now that we have a liquid, as the liquid heats up, once again, our kinetic energy or energy of motion is increasing. As our liquid turns into a gas or vaporizes, what's happening here is the particles are not moving any faster, but they're spreading apart to go from a liquid where the particles are fairly close together to a gas where they're very far apart. So the potential energy once again, is increasing. And finally, as our gas heats up, the particles are moving faster and faster and faster as it heats up, and the kinetic energy, once again, is increasing. Okay, so just make sure you have those labeled on your graph. And now I just want to go over the difference then between how you would know if you had a pure substance as opposed to a mixture. So, what we see with mixtures is as we heat something up, the temperature keeps increasing. You don't see those plateaus as you go through boiling and as you go through melting. So, just know that we don't see the plateaus. And I just want to show you a picture of that. Here, the black line is for a pure substance. You see a nice plateau as it changes state. A mixture would not flatten out completely. It would just, the temperature would keep increasing throughout. And what we would also see is that if we were talking about the melting point, that the temperature where it was melting would actually be lower. Now, one other thing I want to point out is what I have shown you is a heating curve. Now, at the top of this screen, I'm just going to kind of just draw a cooling curve for a pure substance. So here, if we had a pure substance and we're cooling it instead of heating it, what we would start with is we would start with a gas. If it starts as a gas, if it were pure substance, it would flatten out. And then we would be cooling down a liquid. And then as it freezes, it would flatten out if it were a pure substance. And then we would be cooling down the solid. So it would just go in the opposite direction, but it would have the same general shape. And obviously, if it were not a pure substance, we would not have those plateaus just like we see as we heat up a mixture. Okay, so this is the information I want to do on heating curves and cooling curves. So I'm going to stop now and I want you guys to practice labeling the different parts on the worksheet that's in Classroom.